Cryptography is essential for secure communication in our digital world. It involves techniques that transform information into unreadable formats for unauthorized users, ensuring only intended recipients can access the original content. This transformation is achieved through various encryption methods which protect sensitive data against cyber threats. In today's interconnected society, understanding encryption techniques is crucial for safeguarding individual privacy, corporate data, financial transactions, and confidential communications. As cyber attacks become increasingly sophisticated, the demand for robust encryption methods intensifies. By grasping the fundamentals of cryptography, individuals and organizations can better defend against potential breaches and maintain data integrity. This discussion explores various encryption techniques such as symmetric and asymmetric encryption and their applications across different sectors, from securing emails and online banking to protecting sensitive government communications. One of the simplest and most well-known encryption methods is the Cesar Cipher, named after Julius Caesar, who reportedly used it for secure communication. This technique shifts the letters of the alphabet by a fixed number of places. For instance, with a shift of 3, A becomes D, B becomes E, and so on, wrapping around after Z. For example, the message hello becomes cur with a shift of 3. To decrypt, the letters are shifted back by the same number, so cur reverts to hello. While the Cesar cipher is easy to understand and implement, it has significant security limitations. Its simplicity makes it vulnerable to frequency analysis, where attackers analyze the frequency of letters in the encrypted message to deduce the shift used. Additionally, with only 25 possible shifts, excluding a shift of 0, it is susceptible to brute force attacks. While the Cesar cipher is an excellent introduction to encryption principles, it is unsuitable for securing sensitive information today. In contrast, the Vigara Cipher enhances security by employing a keyword for encryption, making it more complex and harder to crack. This process involves repeating the keyword to match the length of the plaintext message. Each letter of the plaintext is shifted according to the corresponding letter of the keyword. For example, with the keyword key and the message hello, the keyword forms key. The letter H is shifted by the position of K, 10, resulting in R. This process continues for each letter, creating a more intricate encrypted message. To decrypt, the same keyword is used, but with backward shifts. The Vigara cipher gained prominence in the 16th century and was widely used for diplomatic communications due to its enhanced security features, though it was later considered breakable with advanced cryptanalysis techniques. Despite its improvements over simpler ciphers, the Vigara cipher is not immune to vulnerabilities, particularly to frequency analysis. This technique studies the frequency of letters in the ciphertext to uncover patterns that can reveal the encryption key. If the keyword is short, certain letters may appear more frequently, allowing cryptanalysts to make educated guesses. This underscores the importance of using strong, unique keys in cryptography. Longer, more complex keys that do not repeat frequently can enhance security, making it harder for attackers to use frequency analysis effectively. Key exchange is fundamental in cryptography, essential for establishing secure communication. Often, two parties want to share a secret key for message encryption, but this becomes complicated if an eavesdropper intercepts the key during transmission. If shared over an insecure channel, the eavesdropper can easily capture it, compromising communication. This highlights the need for a secure key exchange method that ensures confidentiality and integrity. Establishing a secure key exchange is crucial. Without it, even the strongest encryption can be ineffective. One approach involves using public channels for key exchange. Public key cryptography allows secure key exchanges without sharing them directly. Each party has a pair of keys, a public key that can be shared openly and a private key that remains confidential. This method mitigates key exchange risks, enabling secure communication even in potentially hostile environments. Number theory, a branch of mathematics dealing with properties of integers, is significant in cryptography as it provides the mathematical foundation for encryption methods. Key concepts include congruences and modular arithmetic, essential for encoding and decoding messages. Congruences express relationships useful for encryption, while modular arithmetic enables calculations within a finite set of integers, aiding in managing large numbers used in cryptography. The RSA algorithm, one of the most widely used public key cryptographic systems, heavily relies on number theory. It utilizes prime numbers and modular arithmetic to generate keys. In RSA, two large prime numbers are multiplied to create a modulus used in both public and private keys. The security of RSA hinges on the difficulty of factoring this large product back into its prime components. Another example is the Diffie-Helman key exchange, which employs modular exponentiation and discrete logarithms for secure key exchanges over a public channel. Number theory not only underpins cryptography's mathematical principles, but also enhances the security and efficiency of modern encryption methods. Divisibility and relatively prime numbers are fundamental concepts in number theory, crucial for cryptographic calculations. Understanding divisibility helps determine how numbers interact in modular arithmetic, foundational for encryption algorithms. Relatively prime numbers or co-prime numbers are pairs of integers sharing no common divisors other than 1. This concept is significant in cryptography, particularly in RSA, where the security relies on the properties of co-prime numbers. The public and private keys in RSA are generated using two large prime numbers, and the totient function, which counts integers up to a given integer that are co-prime to it, is crucial for key determination. The implications of divisibility and relatively prime numbers for secure encryption are profound, ensuring keys are generated and exchanged securely. By leveraging these concepts, cryptographic systems maintain integrity and confidentiality, safeguarding data against unauthorized access and attacks. Euler's totient function, denoted as Phn, is crucial in cryptography. It counts the number of positive integers up to n that are relatively prime to n. To calculate Phn, use the formula Phn equals sign n times 1 minus 1 over P1 times 1 minus 1 over P2 times 1 minus 1 over Pk, where P1, P2, Pk are the distinct prime factors of n. For example, if n equals 12, with prime factors 2 and 3, then Ph12 equals 12 times 1 minus 1 over 2 times 1 minus 1 over 3 equals 4, indicating 4 integers, 1, 5, 7, and 11, are relatively prime to 12. In RSA, the totient function helps determine public and private keys. The private key is derived from Phn, where n is the product of two large prime numbers. RSA security relies on the difficulty of factoring and back into its prime components, making n critical for secure key generation and encryption. The Diffie-Helman protocol is a groundbreaking method for secure key exchange that allows two parties to establish a shared secret over an insecure channel. The process begins with both parties agreeing on a large prime number P and a base G. Each party chooses a private key. Alice selects A and Bob chooses B. They compute their public keys by raising the base G to their private keys modulo P. Alice computes A equals G to the power of a mod P, and Bob computes B equals G to the power of B mod P. They then exchange public keys. Upon receiving the other's public key, each party raises it to their private key to compute the shared secret. The Diffie-Helman protocol facilitates secure communication without sharing a secret key beforehand, though challenges like man-in-the-middle attacks exist without proper authentication. Additional security measures, such as digital signatures or public key infrastructure, PKI, are often employed to ensure authenticity, enhancing overall key exchange security. In summary, we explored several key encryption methods vital for secure communication in our digital world. We discussed the Cesar Cipher and its simplicity, moved on to the Vigara Cipher for enhanced security, and examined the significance of number theory and Euler's totient function in algorithms like RSA. Additionally, we covered the Diffie-Helman protocol, crucial for secure key exchange. Understanding these methods is essential for anyone looking to protect their personal and professional information in an increasingly interconnected environment. Cryptography has real-world applications impacting our daily lives, from online banking to secure messaging. We encourage further exploration of cryptography and its applications, as it is a fascinating, evolving field. If you found this video informative, please consider subscribing, liking the video, and sharing it with others. Your engagement helps us create more content and fosters a community eager to understand secure communication in today's digital landscape. Thank you for watching.